Good evening, everyone. Welcome to the fifth discussion hour of this course on robotics. This week, we will be discussing the kinematics and statics of manipulators. We will see how we can find relations between the joint angle velocities and the velocities and the angular velocity of the links and the end effector. And we'll also see how to find relation between the forces at the end effector and moments at the end effector, and how do they relate to the joint torques that arise in the uh, manipulator, right? So I will start the discussion uh, with basically first stating the agenda for this discussion hour. First is what we'll see: velocity propagation in serial. Then we'll see what are Jacobians, and then we'll see force propagation for static case. And the central character of this entire discussion would be the Jacobian. And as we'll see, and you might have already seen in the lectures and the lecture slides, that Jacobians are central to whatever we do with the manipulators, be it kinematics or statics. So let's get started with the kinematics. So in kinematics, we discuss about two quantities. First is the linear velocity and the angular velocity. So first we will discuss how to find the angular velocity. Now what we know till now is we know the orientation of the frames, right? So basically this is the, as we have been doing till now, we assign frames. This is the fixed frame, then let's say this is the first link, then this is the second link, and so on and so forth, and this is the, let's say, the last link which has the end effector, right? So at each link, at each joint, we assign the frames, right? Finally up to the tool frame, basically the tool frame. and other frames are numbered serially from 1 to n basically. So this is a NDOF, serial manipulator. Okay, so we know the orientation of the frame, and orientation is expressed in terms of as the rotation matrix. R, right? So for frame I, the orientation so for frame I, the orientation with respect to the base frame or the world frame, that is 0, that we express as R 0 and I, right? So this is the expression of the orientation, and yeah, and this would be a function of, the elements would be a function of all the joint angles up to that frame. So it would be like containing terms having cosines and sines of theta 1, theta 2 up to theta I. To theta I, and also of course the link lengths n1, n2, and up to L I minus 1. So it would depend on these quantities, right? Now, as you would have seen in the lecture slides, we need to find the angular velocity, and we cannot just differentiate the you know the orientation to get the angular velocity, right? So it does not work out like that. There is specific mathematical reasons why it does not work out like that, because the space of orientation is different. Orientation lies in what we call as the SO3 space, and so orientation, this belongs to the SO3 space, special orthogonal group. So these rotation matrices belong there, right? So unlike linear velocities where we can just take the derivative of the position vector with respect to time and we get the velocity vector, but it's not that once we have the let's say functions for Euler angles, and we can just take derivative of those functions and we'll get the angular velocity. It does not work out like that. So there is a relation which I'll not be deriving here, but the relation is something like this, that the angular velocity, and this is the angular velocity matrix, it's a skew symmetric matrix. I will just describe here. So this will be used to denote the angular velocity matrix, and it's a skew symmetric matrix. The property of skew symmetric matrix is that the transpose is the negative, right? And it looks something like this. So the diagonal terms would all be zeros. This would be omega x, omega y, omega z, and here it will be the negative of that. So this is, and you see that this matrix is completely known if we know omega x, omega y, omega z. So this is written also as skew of the omega vector, right? And omega vector is in turn called as the axial of the skew symmetric angular velocity matrix. So just we can keep this in mind. So this is the matrix, and we are describing the angular velocity of the ith frame expressed in the 0th frame, and this is defined as in terms of the rotation matrix and its derivative. So this is the derivative of the rotation matrix, and this is the rotation matrix, and we take its transpose. So this is the relation. If I know the rotation matrix describing the orientation of frame I with respect to frame 0, and I know the rotation matrix means that I know the expression for the elements of the rotation matrix, which would be in turn function of theta i's and li's, then I can basically use this definition to find the angular velocity. And we will show this in case of a simple 2R manipulator, that this in fact holds. Okay, so let's jump into that. So yeah, so I will just add a comment here. So this angular velocity matrix gives the angular velocity in the space fixed frame, that is in frames, right? So that is an important point. There is an alternate variation in which we can get the velocity in a body fixed frame, right? So there the basically the order of this multiplication switches around, right? But mostly we are in general we will use this expression of the angular velocity matrix. Okay, so now let's recall our 2R manipulator. We would be going to our 2R manipulator many times in this discussion hour. And this is the convention which I will follow in this entire discussion hour. So I will just draw this figure with all the frames once here, and we will keep on referring to this convention throughout the discussion hour. This is frame 0, this is frame 1, this is frame 2, and this is the tool frame, okay, at the end effector. This angle is theta 1, and let me write it this side. This is 2, and this is theta 2. Right, so this is the R2R manipulator. Yeah, Nina. So I'm not currently discussing it because uh, that requires little bit more preparation and analysis on my side. So right now I will discuss this first the week 6 material, and if you have like any specific queries or any specific parts of week 5 that you would like to discuss, then that would be helpful for me to exactly uh, and focus on that specific part itself rather than focusing on things which are not directly continued onto the subsequent lecture slides, because week 6 material is something which we build upon, keep on building upon in the subsequent lecture slides. Week 5 is mostly like a standalone kind of a thing. Yeah, so continuing back to the point where we are at. So this is our manipulator, 2R manipulator, and first we'll write the rotation matrices. So the first frame's rotation matrix can be written as, we all know, that is cos theta 1 minus sin theta 1 sin theta 1 cos theta 1 0 0 1 0 0, right? And this rotation matrix would be cos theta 1 plus theta 2. Recalling the convention, this is cos of theta 1 plus theta 2, then sine 1 2 sine 1 2 and cos 1 2. So this is the other rotation matrix, and rotation matrix of 3 is same as rotation matrix of frame 2, because there is no change in orientation between rotation matrices 2 and 3, so this remains the same. C12 S12 S12 C12 0 0. Now let's say we want to find out using this expression the angular velocity of the tool or the third frame which I have written here. I will keep it referring to as third frame or the tool frame, right? Yeah, sure, Ninad, you can let me know once I wrap up today's content, and we can have a look there. So first we'll need to basically, if I want to find out this, right, so I would need to find the derivative of the r dot and r transpose, right? So you can follow along with me. And so these are very fundamental things, and we just want to prove it, or not kind of prove it, but see by doing it that it actually holds up for these simple systems. We can quickly find out and see, and that gives us, a kind of sense of a satisfaction that yeah, this holds up. So that's what we are doing, because it's very straightforward to write the angular velocity of uh, the end effector. So basically omega 3 is very straightforward to write. That's 0 0 and theta 1 dot plus theta 2 dot, right? So this you can almost write trivially, but it's good to know, that how does a general, using the general formulation also, we arrive at this simple solution. So yeah, so let's first write here r dot, right? So r dot is basically, we are differentiating the terms of the rotation matrix with respect to we are taking the time derivative basically, right? So for taking time derivative, we would be differentiating them first with respect to theta I, and then theta I would be differentiated with respect to uh, time, right? So if we do it something like this, so r dot, I think it would need more space. Okay, let's see. So, or we can just first do for a term, right? So what we want to do is, we want to do d by dt of, let's say, cos. How can we do d by dt of cos theta, right? So we can do first d by d theta of cos theta, and then we do that using the chain rule. Basically we do d by d theta by dt, right? So this we write as minus sine theta, and this we write as theta dot, right? So similarly d by dt of cos theta 1 plus theta 2 would be written as, so first we will apply chain rule, right, with respect to this entire thing, let's say, right? You can write it as phi, right? So it will be minus sine phi, and this will be phi dot, right? And this will be minus sine theta 1 plus theta 2, and phi dot is theta 1 dot plus theta 2 dot, right? So this is minus s12 theta 1 dot plus theta 2 dot, right? This is how we will take derivative of the terms in the rotation matrix R03. So this first term, now I'll quickly write all the terms. So this would be s12 theta 1 dot plus theta 2 dot. This will be minus c12 theta 1 dot plus theta 2 dot, this is 0, this is again c12 theta 1 dot plus theta 2 dot, and this is s12 theta 1 dot plus theta 2 dot, this is 0 0 0 1. So this is r dot, and this needs to be multiplied with r transpose. So r transpose would be, so it would be c12 s12 would come here, minus s12 would come here, and c12. So now let's multiply. What you can see is that we can take theta 1 dot plus theta 2 dot common out of there, right? And then we can basically multiply, and here I have missed one minus sign. So c12 minus s12 minus c12, okay. Wait, let me, oops. Did I get it? Transpose incorrect. Why you think so? This is right. This is the rotation matrix. This we have to take transpose, and I think few things got erased. This one got erased. This one got erased. This one got erased. Okay. And so transpose of this would be, this first row would become the first column, and so on, right? So we can write basically here r transpose 0 3, and then here I can write using the full space available. So this would be theta 1 dot plus theta 2 dot, right? This would be minus s12, this would be minus c12, then c12 minus s12, 0 0 1 0. Okay, and and the transpose, right? So transpose is c12 s12 0, and this would be minus s12 c12 0 and 0 0 1, right? So this gives us let me write it here. This should give us theta 1 dot plus theta 2 dot and let's multiply. Okay, so first row, first column, minus S12 C12 and plus S12 C12, so this is 0. Then first row, second column is minus S12 square and minus C12 square, so that is minus 1, and then third is 0. Okay, and then we have next row, that is second row, first column, C12 plus S12, that is 1, then C12 S12 minus, that is 0, and then 0 0 0 0 and 0 0. Yeah, right, I think here I have made a mistake. I will correct it later. And here the term would be 0 0 and this would be this is 0 0 1 0 0 1. Here it would be not 1 but 0 because it's a derivative, so here it would be 0. Okay, so what we have here now, here I made a small mistake. For the indices. So this is omega z and this is omega x. Okay, so if you compare with this, the matrix that you have got here is theta 1 dot plus theta 2 dot 0 minus theta 1 dot plus theta 2 dot 0 0 0 0 0. So this perfectly fits into the skew symmetric matrix definition, right? And this is, if we write this is omega z minus omega z and omega z, right? So this is our matrix, right? And omega 3 0 vector is basically axial of this matrix, and this is basically given as 0 0 and theta 1 dot plus theta 2 dot transpose. It's a 3 cross 1 vector, right? So any doubts still here? So what we just saw is that we verified the expression to find the angular velocity of any frame that we have attached to our manipulator, and it's not that it's applicable in just this case. This is true for any rigid body motion, any point on a rigid body to which this frame is attached, and we get the angular velocity of that frame with respect to the base frame. So for an n degree of freedom manipulator, the end effector's angular velocity would be just theta 1 dot plus theta 2 dot plus theta 3 dot and so on, given that all the so you can add it up if all z axes are parallel starting to beginning, which is in the case of a planar manipulator. For a non-planar manipulator, we can still do addition like that, but we'll have to take care of the vector addition and properly transform them to get the velocity in the correct frame. So for, let's say, similarly, you can do this exercise if you just solve some bigger matrices. So it will be for a 3R manipulator. You can do this exercise and find out that this is equal to 0 0 theta 1 dot plus theta 2 dot plus theta 3 dot. Okay, now that we have the angular velocity, what we can okay yeah, so this skew symmetric and axial, these are basically, you can understand as two mathematical constructs. Okay, so why mathematical constructs? Because when we are dealing with rotations, these two entities basically come up. So first is this skew symmetric matrix, right? So skew symmetric matrices are satisfying this relationship, right? That transpose of that matrix is equal to negative of the matrix itself, right? Now if you basically do the you take a matrix, let's say 3 by 3 matrix with all 9 distinct values, and then you use this relation, so you will get that the diagonal should be 0 and the other 3 elements, right? So only 3 elements you would need, because the transpose needs to be minus of this, right? So you just can describe a skew symmetric matrix by 3 elements, right? And that is useful and important because in this Euclidean space, we describe angular velocities using 3 components itself. So this capital omega, when we compute, it has this property. You can see that this other two omegas are 0, right? The diagonal is 0, and this is minus omega z, and this is omega z, right? So that's why I said that this omega that we calculated fits into the description of the skew symmetric matrix that I wrote here, right? In the 2R manipulator's case, it so happens that omega y and omega x are 0, right? But let's say for any general 3D rigid bodies motion, you can get other terms as well, non-zero. So that is the skew symmetric matrix part. And if I give you this matrix and I say what's the angular velocity of this body, then you basically, what I mean to know is that give me these 3 values, omega x, omega y and omega z, in terms of a 3x1 vector, right? So basically, let's say if the matrix is 0 0 0, and let's say the matrix is -1 2 -3 1 -2 and 3, right? If this is, let's say, a matrix A, then the axial of A, so axial is basically, you can think of as a function which takes in a skew symmetric matrix, right? And what it gives me is that these 3 values, and these 3 values arranged like this, that is 3 2 1, right? So this is the x part, this is the y part, and this is the z part, right? So when I say that this is a skew symmetry matrix, now give me the axial of it. You just take this component and minus of that, this component right here, and again this component minus of that. Right, so this gives me the axial, and back from this axial to skew, we use the skew operation. So this skew of A, that is this again matrix form, right? So the good thing about these is that, you know, when we will see going ahead that we have expressions like this in kinematics, right? Omega cross r we have to do. So there, this cross product of two vectors can be very easily written as a matrix multiplication of this matrix and this vector, right? This r vector and this. So this will be 3 cross 3 and this will be 3 cross 1. So the result will be still 3 cross 1 as in this case. But you know, it just sometimes becomes convenient to write in terms of matrix multiplications and not separately use a cross product operator. So let's say while programming things, you can just keep them as a matrix multiplication and you need not, you know, actually implement the cross product as a function, or maybe use that separate function. So yeah, depending on the need of the formulation, we either write omega in as a 3 cross 1 vector form, or for doing computations we write it in that skew symmetric form. Okay, so that is the story about the axial and the skew part. Okay, so let me know if your doubt has been cleared so that I can move ahead to the linear velocity part. Okay, so let's go to the derivation of the linear velocity, and you know how the relation between the linear velocity of the links can be found out. So let's say for let me start from a new page. So first we will see that, let's say this is a general rigid body, right? And we have a fixed link here, fixed frame here, right? Then we have a frame with it which is fixed to the body, right? So this is 1, and there's a point P, right? There's a point P, and basically the position vector from here to here is given as r01, right? And then this body has some angular velocity omega, right? Omega, that is, so this frame basically, seen from this 0th frame, this frame is rotating with an angular velocity omega, right? So now let's take the first case, right? When this body is not rotating, it's just translating. So it's By translating, I mean that if this is origin of 1 and this is origin of 0, then origin of 1 is moving as seen from origin of 0, right? So for pure translation, it is very straightforward to write, right, that v of 1 in 0, that is equal to basically d by dt of r, right? So basically r dot 0 1, okay, this is the linear velocity, right? And then if there is for general motion, translation plus rotation, right? So the body is moving and it is also rotating about certain axis. The frame one that is fixed to the body, that is rotating about a certain axis, right? So then the velocity of point P, right? And yeah, so in this case, this is the velocity of 1, and then since it's a rigid body and the distance between O1 and P is not changing, so Vp is same as this, right? Because sitting on the O1 point and assuming that it's a rigid body, right, one single rigid body, then the distance between O and P is not changing, right? So their relative velocity is 0. Let's say if this is a, you know, deformable body or something like that, then that assumption does not hold, right? So the distance between O and P can also change with time, and that component will also add up in the velocity of point P. But we are not concerned about deformable bodies right now, we are concerned about rigid bodies, right? And for translation plus rotation, the velocity of point P, so that basically is, so first we write the velocity of point O1, so that is v10, and then we write the velocity of point 1 in P, right? So this will be r dot 0 1 plus this is omega, right? Omega cross r 1 P, right? Basically omega cross the distance, the vector from omega cross the vector from O1 to P, right? R P1, right? So this is the expression for the linear velocity. So this is the expression for the linear velocity. Note that how, so rather than memorizing these formulae, a general tip that I can give is to understand how this expression has been written, right? And if you understand that, then it is much more reliable to, you know, just quickly think through and write these expression in different kind of settings rather than remembering and you know, trying to fitting in other scenarios. So once again, going through the logic part here, it's very algorithmic. So we have the fixed point O, then we have a body, we have a frame attached to that body, that point is 1, and then we have the point of interest, right? The point of interest is basically our point P, right? Now point P basically is fixed, it's not changing its position with respect to frame 1, in the sense that if I sit on frame 1, then I do not see P to be moving away from me. Okay, and the body is rotating about omega with angular velocity omega, right? So first what we do is we write the uh, velocity up till point 1 with respect to 0, so that is r dot part, at how fast the origin of frame 1 is moving with respect to O or 0, and then we factor in the angular velocity part, where we write the angular velocity cross with the position vector from the point 1 to the point P. It's omega cross r, there we write. Okay, so these two expressions of so this is the general relation for linear velocity, and above we saw specific to the arm or serial manipulators how angular velocity can be written. So these two expressions can be written in a recursive form. Basically, since serial manipulators, we can do numbering of the links from 0 to 1 to n. We assign frames and assign numbers to those frames. So we can write these expressions in a very algorithmic form recursively. So recursive formulae for angular and linear velocity propagation. Right, so the angular part would be that omega of the ith frame expressed in the 0th frame is omega of the I minus 1th frame plus the axis about which the ith frame is rotating and how fast it is rotating, right? So this is how you should understand the expressions. Basically, it's no, you should, while using it, you should think and describe each of the terms. And the linear part is basically that the velocity of the origin of the ith frame in the 0th frame, that is velocity of the origin of the I minus 1th frame, and then we have the angular velocity of the I minus 1th frame, and then cross with the, here we use a rotation matrix for change of frame from I minus 1 to 0. Since what the expressions that we are writing right now, these are frame dependent, these have the information of frames. It's not a frame independent equation anymore. What we wrote above is a frame independent equation, right? So, and finally we have the origin location, right, in the I minus 1th frame, right? So this is the last part. You just see this additional rotation matrix because we want to convert the description of this origin of ith frame in the I minus 1th frame to the 0th frame, because every other term we are adding in the 0th frame, right? So these are the, so I would vary from 1 to n basically, and this propagation is done outward propagation. So basically velocity propagation is done outward, and as you will see, force propagation is done inward. So first we propagate the velocities right from the base link to the tip to the end effector, and for forces and moments we start from the tip and then we propagate towards the base link. Let me know if there are any questions here. Okay, so what I just described right now was the deduction. So I will just go through it once again. So I hope this part is right, how we are writing this is clear, right? If that is clear, then we can basically apply the same thing in a serial manipulator's case. So let's say if I draw these links, right? So, and this is here, right? So let's say this is the frame here, this is the ith frame, right? And then we have here the I minus 1th frame, right? Now recursive formulation we are giving at, so when we write in general, we assume that we have all the information, we have computed everything up till the I minus 1 stage, right? So we have every information till here. So we know that the velocity of this frame in the base link base frame is basically this, right? We know that. Okay, and then if I know the velocity of this, now if you just sit on this joint, then what you see is that this link is rotating with omega I minus 1, right? And this distance is basically your O I minus 1 and I, right? The position of the origin of the ith frame with respect to the I minus 1th frame, right? So now if you sit at this joint, this I minus 1th joint, then what you see, and when you see the ith joint, you see that ith joint is rotating. It is at a distance of this from you, and it's rotating with this angular velocity, right? Since there are no prismatic joints and it's a rigid link, the distance between these two is not changing, right? So the velocity that I would see if I sit at I minus 1 edge joint is this, right? So this is the velocity of OI, which I will see if I sit on I minus 1th joint, right? That is this part. And now since I want to know with respect to the base, so to find it with respect to the base, what I do need to add? We need to add the velocity of where I am sitting, that is OI minus 1 with respect to base, right? And that gives me velocity of OI with respect to the base. Does this make it clear how velocity is getting? Okay, linear velocity part, right? Angular velocity part, it's like you are just, so this joint is rotating with theta I minus 1, and then the subsequent joint is rotating with theta I. So, and the axes are all let's say doesn't matter about the axis. So basically you can keep on just adding the angular velocities. That is the angular velocity part, the most straightforward part. And this is how you can understand the linear velocity part, that you sit at joint I minus 1, you see joint I, you see that the joint I is rotating is at a fixed distance from you, and it's rotating at given angular velocity omega I minus 1, the angular velocity of link uh, the angular velocity of link I minus 1. And the second term of this expression is contribution to the velocity as seen from I minus 1 frame. And then since I have to generally write velocities with respect to the base of the end effector of the manipulator, so I have to add whatever velocity I have computed for I minus 1, right? And this process would start from, as I said, I is equal to 1. So for I is equal to 1, it would be V0, which is 0, right? And this only this term would be there. So the very first, right, for I is equal to 1, for I is equal to 1, it means that this is the base that is attached, and this is the first link, right? This is the first link. And this is the first frame, this is the 1th frame, right? Now the 1th frame origin is coincident with the 0th frame, right? So 1th frame origin, this is the 0th frame, right? So VO and O1, so that will be equal to 0, right? Because the origins are also coincident, and since so and the it's also not shifting the origin of frame 1, it's also there. So this first term is 0, and this OI with respect to I minus 1, that is also 0, right? So this is 0 because V0 1 is 0 and O0 1 is 0, right? So first is 0, and you know that, right? Okay, very good. Now comes the at the base of the second link, you have this, right? In fact, I will derive this for a 2R manipulator right away itself, so that will make things much clearer. So this is the second frame, right? Now for the second frame, what you will write? You will write V02 or O2 is 0 for O1 plus the angular velocity of the first link, that is omega 1, cross the rotation matrix from 1 to 0, and this is basically the expression from of the origin of the second and the position vector from the origin of the first frame, right? So this is it. Now this part is 0 because we found out in the first step of the recursion. So the second link's velocities expression would be this. Right, and similarly, if there are more number of links, you just keep on doing this process, right? So again, just take a couple of minutes and let me know if this is clearer now. This is O2. Wait, I think they are still. So I will move on to this derivation for a 2R manipulator, and that would, I believe, clear out the remaining doubts. So let me just proceed on to that, and let's see if there are some queries after that as well. since I will derive all the rotation matrices and write all the values also there, it would be clearer. So again, just recall this convention that we are using. Frame 0 is fixed, frame 1 is rotated angle theta 1, frame 2 is rotated with respect to frame 1 with theta 2, and the tool frame or frame 3 is basically parallel to frame 2. Okay, so we now do the velocity propagation for a 2-hour manipulator. Right, so we start the first equation we already have done. Let me write it once again for completeness sake. So I will vary here from I is equal to 1 and I is equal to 2 and I is equal to 3. Right, we have 3 frames, right, for which we want to write the velocities. 0 is the base frame, right? So first would be v0 001, right, that we just saw, and this will be v00, right, plus omega 0 0 and o o or I should write the entire thing. So right, so it would be just 0 0 and then o 1, right? So what we just, so here all these are 0. The origin of the base frame is fixed, so it's not moving. Origin of the base frame 1 and frame 2 are coincident, right? So origins of frame 1 and frame 0 are always coincident. Okay, so this is 0, so this entire thing is 0 vector. So first frame is done. Now let's go to the second frame. So second frame we'll write v0, then here we'll write o2, then 0 01, the previous origin, plus angular velocity of the first link expressed in the base frame, and then we have the position vector to the origin of the second frame in the first. I think that was written what I wrote here, and then we convert 1 to 0, right? So this, since we are writing it in the frame 1, we need to convert it to make it consistent with the other terms, so 1 to 0, right? Now this is 0 as we derived here, so that part is gone. Now what is the angular velocity of link 1 in the base frame, right? So So this link is rotating about the z axis of the base frame with angular velocity theta 1 dot, right? So this will be 0 0 theta 1 dot, right, and cross with, and this you can also write as basically theta 1 dot z0 cap, right, cross with, now what is the rotation matrix from 1 to 0, right? So it will be c1 s1 s1 c1 0 0 1 0 0, right? So we'll write here c1 s1 s1 c1 0 0 0 0 1, right? And what is the position vector of origin of frame 2 in frame 1? So if you will see here, remember, so along this, right, this is frame 1 and this is frame 1's x-axis, so this is x1 hat, right, and we have, this is L1, right, length is L1. So origin of frame 2 is at a distance L1 along the x-axis of frame 1, right? I will repeat, origin of frame 2 is at a distance L1 along the x-axis of frame 1, right? So if I just write this, so this is L1 x1 hat, right? So that means L1 0 0, right? So that's what which comes here. Okay, so now we have basically theta 1 dot cross with, right, we can quickly do the multiplication, so it becomes L1 c1, then L1 s1, and then 0, right? And this is in the 0th frame, right? This is in the 0th frame, so we can write it in using the unit vectors of the 0th frame. This is the first vector, and we have to cross with the second vector, which is L1 c1 x0 plus L1 s1 y0, and z is 0, right? So now take the cross product, so it becomes L1 theta 1 dot c1, and z cross x is, what is z cross x? Minus y, within the right hand rule. Oh no, x cross y is z, y cross z is x, and z cross x is y. Okay, so y, right, and plus with, this is L1 theta 1 dot s1, and this is minus x0, right? So writing it again in the vector form, this becomes L1 theta 1 dot s1, and this is L1 theta 1 dot c1, and this is 0. So this is what This is velocity of origin of frame 2 expressed in frame 0. Any doubts here? Take a couple of minutes and go through it once again. Okay, so this is till frame 2, but remember that we need to basically find of frame 3, that is the tool frame or the end effector frame, right? So we have one more to go, right? So the third one again, so this is very algorithmic, again doing the same thing. 0th frame we want to express the origin of third frame, that is equal to origin of second frame plus the second link in the base frame, then the rotation matrix from this to this and this to this, right? I hope you are more confident now in writing these expressions, right? And writing while consciously thinking that what each terms mean. So now we know this part, so I will just let it be for now and focus on the second term, right? So again, this part is known, so this is 0 0, and this will be theta 1 dot plus theta 2 dot, right? Then the two z axes are parallel, so this is theta 1 plus dot plus theta 2 dot in the base frame, right? Now we have this, the rotation matrix from second frame to 0th frame, so that is C12 minus S12 S12 C12 0 0 1 0 0, right? And this would be, again, it's at a distance L2 along x2, so this is like this, right? So this term is minus L1 theta 1 S1 minus L1 theta 1 dot S1, this is L1 theta 1 dot C1 0, this is it, then 0 0 theta 1 dot plus theta 2 dot, so this is, again it will be L2 C12, then L2 S12 and 0, right? And this will again give minus L1 theta 1 dot S1 L1 theta 1 dot C1 0, okay, and plus with, so again this is a z, this is the z0 term, and this is x0 term, this is y0 term, so same cross multiplication like this, so there will be one term in y and one term in minus x, right? So it will be minus L2 s12 theta 1 dot plus theta 2 dot, and the y term will be positive, so L2 C12 theta 1 dot plus theta 2 dot, and this is 0, right? So the final velocity of the tool frame or the third frame's origin can be given as L1 theta 1 dot S1 minus L2 S12 theta 1 dot plus theta 2 dot, right? This is L1 theta 1 dot C1 plus L2 C12 theta 1 dot plus, and 0. 0 in the Z component makes sense also because this is a planar manipulator, so nothing is moving outside or inside this plane of the paper basically. So the end effector has velocities in x and y direction, which can be written like this in terms of the lengths and the joint angles and joint velocities, right? Any doubts in this process of doing velocity propagation? L1 C1 x0, where no, this is, so L1 C1 x0, right? This is the first term of this vector. When you do cross product of theta 1 z0 with this term, so the scalar parts gets multiplied, so that is L1 theta 1 dot C1. Then z cross x is y, right? So y is the unit vector that comes, and when I write it again in this column vector form, so this term comes in the second index because this is corresponding to the y component. And the second term here, we do z cross y, so that gives us minus x, and that with sign comes here in the first index corresponding to the x0. So all velocities, this velocity that we have derived, this velocity that is of origin 2 with respect to base, this is origin 3 with respect to the base, right? What we did here, this one would be this one would be the velocity of origin of 2 with respect to velocity of origin of 1 expressed in the base, right? That is the significance of this term, that velocity of origin of 2 with respect to origin of 1 expressed in the base frame, right? So I think just to add on, which I believe sometimes gets a little bit confusing working with vectors and frames, is that there are two things which you describe or let's say convey when you describe or say these vector quantities, right? One is that what is that vector, right? What does it represent? So that is, let's say I am saying this vector represents the velocity of frame 2 with respect to frame 1, right? Now when I say this gives me what information does that vector convey, right? Now when I have to do computations, I have to write that vector or express that vector in a specific frame, right? And that's where we need to state that which frame we want to work in, right? So I can write the velocity of frame 2 with respect to frame 1 in either frame 2 or frame 1 or frame 0 or any frame that I assign anywhere else, right? And that description would change, but essentially physically that vector remains the same, right? So what I mean is that if this is frame 1, this is frame 2, right? Then let's say if this is the position vector, this is the position vector of frame 2 with respect to frame 1, right? When this is the notation that is usually followed when vectors are written without describing which frame they are expressed in. This is called as the frame independent notation. Now when we are doing computations, of course we need to write the elements of those vectors, and when we need to write the elements of those vectors, then we want to specify a frame that okay, this is this, and generally at that time we put a square bracket around, right? That this is, let's say, 2 1 and expressed in the 0 frame, right? 0 frame might be somewhere here, or expressed in some other frame, either 1 2 or some other, some other frame. And so that's the the key thing. What you see here is the description of the velocity of the origin of frame 2 with respect to frame 1 described in the base frame, right? That's why I stressed on this superscript here. So finally what we have derived here is the velocity of the end effector or the tool frame described in the 0th frame, right? Now the same thing can be described in any other frame you want to write it in. You can describe it in the, and one common is to write in this in the 3rd frame itself, right? So v3, right? This, how to write this, that the velocity of the tool or the end effector in the end effector frame itself, right? So then what changes is that basically we can directly use rotation matrices, right? So we know the orientation of the 3rd frame with respect to the 0th frame, and we basically do the appropriate, so this rotation matrix from 3 to 0, right? From 3 to 0 is C12 minus S12 S12 0 C12 0 1 0 0, and the opposite transformation will be taken care by the transpose of this, right? So this is C12 S12 minus S12 C12 0 0 1 0 0, right? Now if I multiply this here, pre-multiply this vector with this, then I get in 3rd frame. Okay, so now what we need to do is that this description of the end effector velocity that we wrote, now we can write it as a matrix times the joint velocities, that is θ1 dot and θ2 dot, right? So we can reverse engineer that. So θ1 dot gets multiplied with the first term here, so collecting the terms with θ1 dot here, it gives us minus L1 S1 minus L2 S12, so minus L1 S1 minus L2 S12. With respect to θ2 dot, we have one term only, that is minus L2 S12. Now second term, so with respect to theta 1 dot, we have L1C1 and L2C12. And with respect to theta 2 dot, we have L2C12. Right. So if you multiply, you get back the same thing. Now this matrix that you see here, right? This matrix that you see here, this is a very special matrix. This is the Jacobian, right? Jacobian of the end effector with respect to 0, and this is expressed in the 0th frame, right? So basically this multiplied with the joint velocities gives us the velocity of the end effector in that specific frame. This is what we call as the Jacobian. And this is for a 2R manipulator. And Jacobian can be computed for any mechanism, right? And Jacobian is one very important point. Jacobian is frame dependent, right? So let's say the same theta dot, right? Theta dot remains the same. If I multiply it with a Jacobian, again Jacobian from, let's say, the of the end effector, Jacobian of the end effector, but expressed in the base frame, then I get the velocity of the end effector in the base frame. If I multiply with the Jacobian expressed in the end effector frame, then I will get velocities in the end effector frame, right? So Jacobian is frame dependent, so be very careful while using Jacobians, right? So this matrix that we got here, you can also find it in another way. And basically, if you remember, this is the 2R manipulator, right? This is theta 2, this is theta 1, this is L1, this is L2. If this is the end effector with coordinates xp, yp, right, and this is 0, 0, then in forward kinematics we saw that xp is equal to L1C1 L1C1 plus L2C12, and yp is L1S1 plus L2S12, right? Now if I do this del xp by del theta 1, then I get minus L1S1 minus L2S12. Then if I do del xp by del theta 2, we get minus L2S12. And similarly for yp, if I do, I get L1C1 plus L2C12 and del yp del theta 2, I get L2C12. Now if del x by del this matrix, this I can write as del xp del theta 1 del xp del theta 2 del yp del theta 1, and this will have terms L1 S1 minus L2 S12 minus L2 S12 and L2 C12. Right, now if you see, this matrix is same as the Jacobian which we calculated above, right? Just have a look here. So the relation between the linear velocity of the tool and the adjoint velocities is given by the Jacobian, and the Jacobian can also be basically derived, where we can arrive at the Jacobian by doing the differentiation of the position of the end effector with respect to the joint angles, right? So this is Jacobian. So what does Jacobian give us? It's, let's say, if we know the joint velocities and we know the joint angles, that is, what is the configuration of the manipulator, we know the joint angles and how fast are the joints moving, then we can find out what is the end effector velocity. And other way around, if end effector velocity is known and joint angles are known, then we can find out how fast joints are moving, right? So this forward and inverse problem we can solve very easily using Jacobians, right? Any questions up till here? Okay. So now this Jacobian also holds some very important information. So first I should write that we can get the end effector velocity using the Jacobian, and if I know the end effector velocities and the joint angles, then I can basically do the inverse of Jacobian. I will describe why I'm writing pseudo inverse, and then this. So this is forward kinematics and this is inverse kinematics. Now an important quantity that we have is the determinant of the Jacobian, right? So for a 2R manipulator, the determinant of Jacobian is given by, let's do that. So the determinant will be minus L1 S1 minus L2 S12 into L2 C12 and then minus L2 S12 L1 C1 plus L2 C12. And then this will be minus L1 L2 S1 C12 minus L2 square S12 C12, and then it will be plus L2 L1 C1 S12 and plus L2 square S12 C12. So this goes away. In this we have L1 this we have L1, L2, and this will be minus S2. So this is the determinant of J for 2R manipulator, right? Now what we are interested in basically is what angles at theta is equal to 0 and pi J, the determinant of J is basically 0, right? And this is an important concept called singularity, right? So when determinant of J is 0, so that means that J loses rank. For 2R manipulator, this is when theta 2 is 0 or pi, right? So either the manipulator is folded onto itself or fully extended, right? So that is special, two special configurations, right? So this is 2R manipulator, right? So this is the fully extended position, and let's say this is the fully folded position, and it's back like this, right? So this is the limit of the workspace on the closer side, and this is the limit of the workspace on the outer side, bad circle, right? So the singular points are here. This is a singular configuration, and this is a singular configuration. This is theta 2 is equal to pi, this is theta 2 equal to 0, and at these configurations the arm can have velocities. At these very specific configuration, the arm can have velocity only in one direction, right? So at singular configuration, the arm loses 1 degree of freedom, right? It can only have velocity perpendicular to itself. Right, so as you can see, at singular positions we have locked out or eliminated or have less degree of freedom, so we generally want to avoid these configurations whenever we are working with manipulators. So we design our trajectories, and we plan our motions in a way such that we avoid these configurations. The good thing for 2R manipulator is that the singularity or the singular positions lie at the boundaries of the workspace. There is no singularity inside the workspace. So if we just avoid the boundaries of the workspace, we'll be fine. But for other manipulators, it could be possible that the singularity lies somewhere inside the workspace also, and then we have to be more careful for avoiding the singularities. Any questions about the singularities? Okay, cool. Another important metric that we work with is basically we have the expression of the velocity, right? So we have that velocity is Jacobian times L1 S1 minus L2 S12 and then L1 C1 plus L2 C12 then L2 S12 and L2 C12, right? This is Jacobian. So like for 2R you can almost like you can easily memorize this Jacobian. Not to say that you should not know how to derive it, but since it will be used multiple times, so you can memorize it. So now if I do dot product of this velocity vector, right, so I get something like this, an expression where I have terms like this. Right, and what we find out is that these expressions Gij, they are elements of the matrix J transpose J, right? So if we do J transpose J, right, for the J above, the elements that we will get for index 1 and 2, that those elements show up when we do V square, right? Velocities dot product with the velocity itself, those terms show up, and this is very interesting, right? So basically, let's say if we want to, if we have a condition that my joint velocities have to satisfy this criteria, right, and then V square is basically this G11 theta 1 dot square plus 2G12 theta 1 dot theta 2 dot plus G22 theta 2 dot square, right? We have this velocity and this is the condition, right? So what are the admissible set of velocities that we can achieve, right? So we can include that constraint in our velocity and write the expression that basically what we want to achieve is this. And lambda times this constraint that we have, that theta 1 square plus theta 2 dot square minus 1, right? This is our constraint basically, and this is a logical constraint because our in reality our motors, which basically provide the angular velocity to the joint, they will always have constraints on the maximum velocity that they can achieve, and we can write that constraint like this. And then what we do is basically, let's say this is F, so in order to find the solution of this, we do del F by del theta 1 dot equal to 0, and then we do del F by del theta 2 dot equal to 0, okay. So what we finally we get is that del F by del theta 1 dot, so whatever the value of lambda, solving this, solving this we get lambdas, right? We get lambdas. So if you do this, right, we get an equation in the form of, in this form, right? And this is an eigenvalue problem. Now why this is important is that, so just to give you a physical intuition, so Jacobian is basically carries information about the uh, physical length of the links and the angle or the configuration of the manipulator, right? So it has information about the kinematics of the or the structure of the manipulator. And what we are trying to find out is that while satisfying a certain limit on the angular velocities, we would be interested to find out what would be the maximum and minimum velocities that we can achieve, right, in a certain in a certain configuration of the arm. What are the maximum and minimum uh, ang- velocities of the end effector that we can achieve, and in what directions we can achieve those velocities, right? So the intuition here is that for a given configuration of the manipulator, what is the maximum and minimum linear velocity of the end effector, and what directions do they occur in? Like, what is the direction in which you can move with maximum velocity, and what is the direction you can move in minimum velocity, right? So two things we are concerned with. And like, I just quickly mention that thing, that it turns out that we have this matrix J transpose J, this special matrix, and if we find the eigenvalues, which are, let's say, lambda 1 and lambda 2, right, and the eigenvectors for these eigenvalues lambda 1 and lambda 2, then what we find out is that Vmax, the norm of V maximum, is root of lambda 1, given that lambda 1 is greater than lambda 2, and the minimum velocity that can be achieved is root of lambda 2. And this was a case where we have this constraint on the joint velocities. If this is equal to k, then this becomes k times root lambda 1, and this becomes k times root lambda 2, right? And what this specifies is that it specifies an ellipse, right, which has two axes. This is the major axis, this is the minor axis. So this is proportional to root lambda 1, this is proportional to root lambda 2, right? So what happens is that if this is the end effector, then it can move in this direction most easily and in this direction with least ease. So it can move with maximum velocity along the major axis of the ellipse, and it can move with the minimum velocity in the minor axis of the ellipse. So this is where I will wrap up for this discussion hour. So just to summarize, what we have seen today is that we saw how to write the angular velocity first in terms of the orientation of the frames expressed in terms of rotation matrices. Then we described how to write the linear velocity, and we wrote the recursive formula for angular velocity and linear velocity propagation. Then we expressed and we did the process of velocity propagation for a 2R manipulator, right? And then we saw how that the joint velocities and the velocities of the end effector are related through the Jacobian matrix, and many different important information is can be derived out of the Jacobian matrix. uh, One is information about singular positions, and the second and the very last that we discussed today is the information about the directions in which the end effector in that configuration can move with maximum velocity and minimum velocity. So this is where I will stop for this week, and continue from this point itself. Thanks for joining. Okay, I'll just give me 2 minutes. I will drop it in the chat here also. You can open it right now itself and see if you are able to access it. Can you check? I have dropped it in the chat.